Welcome. We're going to be delving into data mining. And one of the applications of data mining that we're going to be looking at is something along the lines of customer segmentation, where we want to understand how certain groups of customers behave. And we want to group customers so that customers within each group behave similarly to other customers within that group, but each group of customers is meaningfully distinct from another group. So if we were just to take the tiny little data set that we have here, 3 observations and 2 variables, I want to place this into a little bit of context. Like, let's pretend that we're an online retailer, and we have data on 3 people, person 1, person 2, and person 3. And these 2 variables, x1 and x2, represent the number of products that they viewed for a given brand on a visit to our website. So person 1 visited 7 products by brand 1 and 5 products by brand 2. Person 2 viewed 6 products from brand 1 and 4 products from brand 2, and person 3 viewed 2 products from brand 1 and 1 product from brand 2. And so it can be interesting or important for a business to look at how customers behave. Try to group them into groups where they behave like other people in that group, and then do target marketing, target product suggestions, trying to provide customers with access to the things that interest them the most, or promotions that interest them the most. So how this relates to data mining is that we have to quantify similarity. We need to figure out a measure that gives us a numerical representation of how similar customers are. We've got a 2-variable example here for a very meaningful reason, and that's because it plots really well on an XY coordinate. So I'll plot these really quickly as a scatter plot. All right, customer views of products by 2 manufacturers, or I said brands before. So X1 will be brand 1. Right, that's how many times they viewed a product by brand 1, and this is how many times they viewed a product by brand 2. Eyeballing this, right away you might say to yourself, yes, these 2 observations, right, observations 1 and 2, are more similar to each other than either of them are to observation 3. Customers 1 and 2, they viewed products by brands 1 and 2 in a much more similar fashion than did the third person. This person viewed fewer of products by either brand. So we quantify how similar or different they are using 2 measures called the Euclidean and Manhattan distances. We're using a 2-case example, but we could use many more cases, right? We've got 2 brands, but we could expand this and group people by include age as a factor or gender as a factor, various lifestyle factors, sports we know they participate in, anything that is relevant to what they might be looking for in a product and how we might reach them. So the Euclidean distance here, it's the first one listed, and that's the one we're going to talk about. It's very commonly used. Basically, the distance between 2 observations is equal to the square root of the sum of the squared differences between each individual across each pair of variables. We square them because we want to keep that positive, and then we take the square root to reduce ourselves back down basically to our original set of units. Whereas the Manhattan distance does the same thing. Looks at 2 individuals and their difference on observation 1. I'm going to rephrase that. 2 individuals and their difference with respect to variable 1, and adds the difference between those two individuals with regard to variable 2, taking the absolute value, again, to keep those positive. We can have as many variables as we need, but what we need to know is that we're comparing two individuals, and we get the distance between two people or two observations. We could be using this to cluster cars into similar groups when it comes to performance and fuel economy and designed use, right? Any two types of things. But they have to be pairwise observations. So we'll compare observation 1 with observation 2, then we'll compare observation 1 with observation 3, then we'll compare observation 2 with observation 3. And we'll get a measure for how far apart each observation is from each other observation. So to start, let's take Euclidean distance. And the way I like to set up a problem with regard to Euclidean distance, because I find this formula to be quite cumbersome, I calculate each piece in the parentheses separately. Then I create the Euclidean distance by taking the square root of the sum of those two things. So let me show you what I mean. We're going to do pairs of variables. So let's see how similar or how different. We're really calculating difference here. What's the difference between number 1 and number 2? All right, so these two individuals. When we think of Euclidean distance also, one way that might help it make sense is that Euclidean distance basically is calculating the hypotenuse here, like a squared plus b squared equals c squared. It's going to be the Pythagorean theorem. So if these two variables, the distance between them is the line as a crow would fly. So we're going to look first calculating the squared distance, or the squared difference between, well, with regard to x1. And then I'm going to calculate the squared difference with regard to x2. So variables 1 and variable 2, the difference with regard to variable x1, so the number of products they viewed for, let's call this Patagonia. Person 1 viewed 7 products by Patagonia, person 2 viewed 6 products by Patagonia. So the square difference in those numbers is going to be 7 minus 6 with that caret and then squared. That distance is 1. We can see that too. We've got x1 here. The difference between person 1's value of x1, right? Patagonia saw 7, and persons 2, they saw 6, right? That's a 1 unit difference. Incidentally, it doesn't matter because we square them. If we wanted to look at person 2 minus person 1, person 2 minus person 1, we'd get the same answer. So the order that we calculate them in is not going to be important because we're applying the square root. With regard to product 2, let's call this North Face. Person 1 looked at 5 North Face products, person 2 looked at 4 North Face products. So the squared difference, 5 minus 4 squared, would be the same if I did 4 minus 5. And then the Euclidean distance is equal to the square root of the sum of these two things. And if we refer back down to this formula, the Euclidean distance is going to be equal to the square root of the sum of the squared difference for each variable we have. This extends to the multivariable case, but we've just got a 2-variable case, so we only have these first 2 expressions. All right, so the Euclidean distance, or the length of the line as the crow flies between these 2 points, is equal to 1.41 units. Well, how similar, what's the difference between observation 1 and observation 3? this person here and this person here? Well, we can tell that person 1 engaged more with both brands than did person 3. And the difference between person 1 and 2's behavior, they're going to be much more, that difference is going to be smaller. They're similar. They looked at a similar number of pages than either of them did, or products than either of them did with person number 3. So let's calculate the distance between person 1 and person 3. So the squared distance with regard to variable 1, person 1 looked at 7 Patagonia products, person 3 looked at 2 Patagonia products. So we square that and we get 25. That's the squared difference between them with regard to how many products they looked at that were produced by Patagonia. For person 2, for product 2, or brand 2, which would be North Face, person 1 looked at 5, person 3 looked at 1, so that squared difference is going to be 16. So if we take the square root of the sum of those two things, the Euclidean distance between point 1 and point 3 is 6.4. That's the distance traveled between these 2 points. And our last one that we'll need to look at, the final pairwise observation, will be between number 2 and number 3. So number 2 looked at 6 Patagonia products, whereas number 3 looked at 2. For a squared difference of 16. Person 2 looked at 4 North Face products. Person 3 looked at 1. For a squared difference of 9. Then the Euclidean distance is just the square root of 16 minus 9. So now we would just say that the distance, that doesn't seem right. What did I do wrong? 2 and 3 squared, nothing. Aha, there it is. Not minus, it's plus. I'll leave that open for a second rather than start recording all over. What gave it away for me that there was a problem was because this is a 6.4 distance and this being a 2.65, it doesn't look to me like this distance is less than half of that distance, right? So it cued me off that there was a mistake and I had just entered a minus instead of a plus. Now it makes more sense because the Euclidean distance between 1 and 2 is 1.41. They're more similar. And the distance between 1 and 3 is 6.4. The difference between number 2 and number 3 is 5. So this gap here, right, between these two people and this person is larger. So if I were to group these just based on similarity, I would say that these two are relatively more similar than either of them are with this person if we're measuring them with regard to how many times they interacted with products by these two different brands. All right, that's Euclidean distance. I'm going to pause and come back. We'll do another video calculating the Manhattan distance.